Hello and welcome to Guessing the Methods exam. This is part 8. You've already seen part 1 to 7, hopefully. If you have, you know these wonderful people are the ones that wrote these questions. If you haven't already, go to the website, find the bit where it says like contact us and send them an email thanking them for all of this, because I think they've done a fantastic job. If you've got any value, let them know. Alright, let's take a look. First question, have a try. Alright, so before we get into it, yes, I have made some mistakes over the last 7 videos. If you go into the comments of each video, you'll see people mentioning small mistakes here and there. Thankfully, I don't think I've gotten any answers wrong. It's just been like weird little mistakes. Sometimes I type things into calculators weird, things like that. So, I value you. Thanks for putting it in the comments, letting me know. Let's get on with it. Okay, so it says normally distributed. So the first thing I do when I see normally distributed is draw a normal distribution. With an average of 4 mistakes per video, that's the middle average 4. It is found that 30% of his videos have less than 3 mistakes. So less than 3. The area under the curve there is 0.3. And then the question is, what is the standard deviation closest to? Alright, so there's a couple of different ways you could go about this. So one way would be, because it's multiple choice, it's a trial and error type situation. So you could go in, type 4 in for your mean, type 3 in for your like less than, and then type these all in as your standard deviations, and if it spits out an area of 0.3, you're done. I'm going to treat this as if it's not a multiple choice question, as if I don't know those values and I've got to find that standard deviation. And I think the way that I'm going to have to do it is by using z-scores. So you should know the z-scored formula, z equals x minus the mean over the standard deviation. So what do I know? Well, not very much at the moment. I know how many mistakes I made. I made 3 mistakes. I know the mean, 4. I don't know the standard deviation, that's the thing I want to know, and I don't at the moment know the z-score, but I can find the z-score. The z-score represents something on a standard normal distribution. A standard normal distribution has a mean of 0 and a little like standard deviation of 1. And then to find my z-score, to compare it against my actual thing here, I use the same area, so 0.3, and then I find out what that little z value is there. So here I am in stat mode. I'm going to go distributions, normal distribution, inverse normal, left tail, area 0.3, and I'm doing it all on my standard normal. So a standard deviation of 1 and a normal and a mean of 0. All right, so a z-score of negative 0.5244. That's the z-score there on a standard normal. So I can put that negative 0.5244 in there. So there it is, negative 0.5244. I can rearrange this for the standard deviation. So standard deviation equals 3 minus 4, which is negative 1, over negative 0.5244. And then I'll just get out my like super dodgy calculator here, and my answer is positive 1.907. So which of these answers is closest to 1.907? That would be A. Okay, like I said, you could have done this just doing trial and error, but I wanted to talk about this. I've seen into the future, and we've got a question coming up that you need to use a little bit of this stuff. All right, celebration, next question. All right, so a really good question here. Go and have a try at it. All right, so I know that Layla wrote this one, and she was doing maths last year, and the external had a question kind of like this, where you had to be able to just interpret words and draw a diagram, and that was one of the hardest things to do. So let's do this. And I'm just going to roughly sketch it and then tidy it up, right? So this is the process that I go through when I do this. PQRS is a rectangle. Okay, PQRS. PQ equals RS, and they equal 2. All right, 2 and 2. Another point, M, is drawn above the midpoint of QR. All right, the midpoint of QR, M is drawn above it. Okay, M way up there somewhere. Let's fix that up. M is there somewhere. Okay. QM and RM equals 4 centimeters. QM and RM both equal. Oh, we've got a house. Okay. Determine value of angle QMR that would produce the maximum area for PQMRS. All right, so we're trying to maximize the area of that thing. Wait, how is it changing shape? What's going on? Oh, okay, so we're told this thing, but we're not told this thing, right? So our picture could be, it could look like this. It could look like 2, 2, 4, 4, like that. But it could also look like 2, 2, 4, 4. These are our two extremes. When it comes to these optimization shape questions, I really like to sort of explore, like, hang on, what's the variable we're changing when we're optimizing? And what do my two extreme values look like? So these are my two extreme values, I guess. This one could be really extreme, right? With with 0, and then it's going to have 0 area. This one could be extreme, but I actually know how extreme. It could only be as long as 8, right? Because if it was longer than 8, then this triangle ceases to exist. All right, all of this picture drawing is a really good idea because it gets you thinking, gets you understanding what's going on, gives you an intuitive understanding. I feel like when I look at these two shapes that I've drawn, the area of this is larger than the area of this. So I feel like my answer is going to look more like that than like that. But I don't know, I could be wrong. All right, so there's my official drawing, right? Be aware in the external exam they give you a bunch of blue paper. If I was in the exam, all that weird drawing that I just drew in 10 seconds, that's all happening on the blue paper and then I'm kind of officializing it somehow. All right, area. The area of this shape is obviously equal to the rectangle plus the triangle. Okay. All right, so let's come up with a way to talk about the rectangle. It'd be useful if I had a variable here, x, right? So areas of rectangles, I can handle that. 2x. All right, what about the area of this triangle? We're given a hint here, and it says determine the value of the angle. All right, so QMR. And I know how to find the area of a triangle dealing with that angle. All right, because that angle is half BC, so 4, 4, sine theta. The area of a triangle is equal to half of this, sine the angle between. Okay, so I can tidy that up a bit because that's 16. Half of 16 is 8. So 8 sine theta there. Now, I think I'm doing a pretty good job because this is a formula for the area, right? And I'm trying to maximize the area. But obviously we have a problem, and this happens all the time with optimization questions. We have an x in our formula and we have a theta in our... We have two variables in our formula, and that's a problem. So I need to come up with some kind of equation that links x and theta. And so when I look at this triangle, I see two sides, I see a third side, I see an angle. 3 sides and an angle. 3 sides and an angle. I think cosine rule, right? So cosine rule says that we're going to have this side, x squared equals a squared plus b squared, a squared plus b squared, minus 2 times bc, 2 times 4 times 4, cosine the angle between them. Okay, I've gone a little high, but you get the idea. Now I can go a little further with this because I can say that x squared equals 16 plus 16, which is 32, minus 2 times 4 times 4, which is also 32. 32 cos theta. And I can say that x is equal to the square root of that. 32 minus 32 cos theta. This is gold. This is a very important thing, right? I had a formula with two variables in it. That was a problem. But I can now represent one of the variables in terms of the other variable. So I can take this and sub it into my area formula for x. So area is equal to 2 times, I'm going to need a bit of space there, square root 32 minus 32 cos theta, close the bracket, plus 8 sine theta. That is an expression for area, and I want to maximize it. Now, if I'm going to maximize this, and I've got a calculator, super straightforward. So I've gone into my calculator and I've typed it exactly as you see it there, but everywhere there's a theta, I've put an x in, right? That's confusing because we were using x earlier. 2 square root 32 minus 32 cos x plus 8 sine x. Okay, well, let's draw it. Whoa, okay, that seems pretty wild. Consider what the x-axis is. The x-axis is the angle. Now, look at my calculator. It's in radians mode. But I don't want to talk about this angle in radians mode. I want to talk about this angle in degrees mode. So let's change our setup to degrees. Okay. Wonder if that changes this thing anymore. Okay, that's interesting. Now, what could my angle be? My angle could be anywhere between 0 degrees and 180 degrees. So, and my view window, my x-axis is just 0 to 4. So clearly that's not going to work. So let's go to 180. That'll do. Let's draw that. Okay, and then it shoots off into space. Now the area of this thing, like what's the maximum area it could be? Well, I said that like if the triangle collapsed on itself, it would be 2 by 8, which is like 16. So let's say the max area could be like, I don't know, 30. Let's change our view window. So maximum is 30. All right, we've got something. All right, let's do a little G-solve here, and we'll look for the max. Beautiful. All right, so I have a maximum angle here. So what I should do now is like make it clear that I've graphed this. You know, mention that I've used my graphics calculator, and then put this point here, 120, and the maximum area, we can see that there, 20.78. All right, this question actually only asks for the maximum angle that produces the angle that produces the maximum area, and that answer is staring at us here, 120. Now, based on the exploration we did, having an angle of approximately 120 is maybe a little bit bigger than the drawing here. This just feels right. This feels like a large area, a maximizable kind of area. And obviously you won't have GeoGebra with you, but I have it, and you can see that our area is obviously 0 when we're here, and then we get larger and larger and larger and larger and larger, and it maximizes at 120 degrees. Pretty neat. So a question that I have, and I'm not going to do it, but I'd love to hear from someone in the comments. I wonder if this question can be done tech-free, because it ends up with a really nice angle, 120 degrees, something that we can deal with. So I wonder if someone was to take this line and then find the derivative of it, let the derivative equal 0 so they can find a turning point. I wonder if you've got the skills to do this tech-free. I don't know the answer. Maybe it's impossible. Maybe it's possible. Let me know in the comments whether it's possible or impossible to do this question tech-free. All right, celebration, last question. Here we go, last question. Have a try, see how you go. All right, so it's kind of a tale of two questions here. First paragraph, deal with that, figure some stuff out, and then second paragraph, deal with that. The first paragraph, you can see normally distributed, blah, 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 blah. And in the second paragraph, you can see this like exactly 16 successful. So we've got normal distribution followed by binomial distribution. A classic of the complex unfamiliar genre, switching from one distribution to the next. All right, that's enough of that. Let's look at this thing here. All right, so we're told that it's normally distributed. So obviously, I would always draw a normal distribution here. And then we're told this interesting thing. There's a 0.76% of trials taking less than a month, and 22.4 something percent took more than 3 months. Also a classic. So this is the picture we have, a normal distribution with area of 0.076 being less than 1, and area of 22.45 being more than 3. If you've never seen this sort of question before, it can really throw you because there's no standard deviation and there's no mean. It's another one of these Z-score deals. So I've drawn myself two formulas here to match up with this and this. Now the x in this formula isn't x. The x in this formula is 1. And the x in this formula isn't x. The x in this formula is 3. Now, again, I don't know the mean, I don't know the standard deviation, but if I use a standard normal distribution, I can find z-scores for both of those. So going into my distributions, I'm going with a normal distribution, an inverse normal distribution. And let's take a look. Left tail, 0.0076 is my area, and a standard normal distribution, so a standard deviation of 1, a mean of 0, I get a z-score of negative 2.4275. So that's a nice little formula here. I can do the same thing here. Another inverse normal, but we've got to go a right-hand tail, area of 0.2245. Been a bit careless there. We'll fix that up. And we get an inverse of 0.7571. Beautiful. 2 equations, 2 unknowns. So I think it's probably easier to rewrite these just as like standard deviation equals 1 minus mean over negative 2.4275. And this one is standard deviation equals 3 minus the mean over 0.7571. So this can just be y equals that, and this can just be y equals that. And we can graph these as 2 straight lines. So there we have it. Y is our standard deviation. X is our mean. 2 of those. Graph them. And hopefully, if we just zoom auto, it'll give us a nice little picture. There we go. Looks like they're intersecting over there somewhere. Let's find an intersection point. Okay, we have an intersection point. Now, like I said, X in this bit is our mean here. So we can write down that our mean is equal to whatever that is. 2.5245 for our mean and 0.6280 for our standard deviation. Great, we know how it's distributed now. We know more about this picture. We know the mean and we know the standard deviation. The last part of this first paragraph says, treatment is considered successful if it takes less than 2.75 months to work. So it's a success if it takes less than 2.75. And it's a normal distribution. We know now what the mean is. It's 2.5245. We know the standard deviation is 0.628. And we're saying, hey, this is successful if it takes less than 2.75. So, calculator, another normal distribution. This time we're trying to find an area, so we're going to do NCD. Alright, so a lower down there, an upper 2.75, and what have we got? A mean of a standard deviation, of 0.6280, and a mean of 2.5245. Okay, that right there is our probability that the treatment is considered successful. A P equal to 0.6402. Alright, questions that are like this, and by I mean like this, the style of complex unfamiliar question that mixes normal with binomial always get to this stage. They always get to this stage where it's like, okay, you found the probability of success using your normal distribution. Now that you've got your probability of success, you can forget about your normal distributions and start thinking about your binomial distribution. All right, so I've taken this number here and I've drawn it in a really silly spot. So let's fix that up. P equals 0.6402. And that's just our probability of success now. So let's look at this second paragraph. The probability that there will be exactly 16 successes in the sample, right? Because the question we're being asked is determine the number of individuals. So we're looking for a sample size. 16 successful treatments, and that's the probability of 16 successful treatments. So the probability that X will be equal to 16 successful treatments is 0.000654. We're also told that the probability of there being 16 failures, exactly 16 failures, let's just write 16 fails. We're told that the probability of exactly 16 fails is 0.1170. Okay, so we've got these two pieces of information. We don't know the sample size. Let's write this up as like a big, long binomial formula. Now, exactly 16 successes. That's equal to the number of trials, 16. The probability of success, 0.6402 to the power of 16 successes. The probability of failure, 1 minus 0.6402 times 0.3509 to the power of the number of trials minus 16. Okay, now what about this thing here? Well, if we treat fails as successes, we can do something pretty simple here. We can say sample size, 16, so N16, and then we treat these failures as successes to the power of 16 times 0.6402 to the power of n minus 16. Beautiful. Two equations, one unknown. Very interesting sort of question. A little bit difficult to deal with, but what we can do is something like a little bit tricky. So stick with me because I'm going to talk it through so I don't have to write everything, right? If I divide this entire equation by 0.000654, that means the left-hand side of the equation will be equal to that divided by itself, which is 1. So in other words, 1 will be equal to this divided by that. If I do the same thing on the second equation, I'll have 1 is equal to this divided by this. So I'll have two equations. 1 is equal to this divided by that number, and 1 is equal to this divided by that number. If I have two equations equal to 1, that means two equations must be equal to each other, which means that I can combine these two equations into the following equation. Ta-da! This portion here is just this equation divided by that, that's equal to 1. This is also equal to 1. I've set them equal to each other because these N16s cause massive issues. But making them equal to each other means that I can do this. Done. And those N16s just vanish. So what I actually have is just an equation with an N in it and an equation with an N in it. I have a feeling that I can just ask my calculator what N is. So I've gone ahead and typed that into my function here on the left-hand side, and I've typed in this into my red one here, and I'm going to draw them both. You can see if I got a little multiply sign in here. Doesn't like it when I do that. Draw that, we get a red one, and we get a blue one. So I've gone in, I've done the intersection already. I get an intersection of, let's take a look here, 40.622222. So assuming there's some sort of rounding error or something like that, because we're looking for the number of individuals in this trial, let's round this n equal to 41. Now you can of course go and check this, right? Because now that you've got a sample size of 41, you can try 41 with 16 successes, put that into a binomial distribution, and you should get that answer, 0.000654. Try having 41 and 16 failures, so that's like 25 successes, and you will find that value right there. There we go, something like that. 16 successes, 41 trials, probability 0.6402. 6.542, yeah, this number right here, 0.000654, etc. And then we can do the same with 25 failures, 25 successes, which is 16 failures. And we get 0.11695. Very close to this 0.1170. All right, I am happy with that. I think that is it. Let's celebrate. All right, that is it. That has been Guessing the Methods exam, parts 1, 2, 3, 4, 5, 6, 7, 8. Thank you very much, as always, to my friends here. I honestly could not have done it without them this year. Got lots on my plate, but having someone write these questions for me, good questions too, has been absolutely fantastic. So go and check them out. Maybe sign your sister up, sign your brother up, something like that. Thanks very much for watching this whole series, or watching parts of this series. I appreciate it. I really hope that you're getting something out of it. It means a lot to me to be able to help you all out in any small way that I can. No doubt you're going to crush your exam on Monday, so good luck for that one, and I'll catch you after. Peace.